Can you hear me now? Yes. Yeah. So, thank you, Nandini, for a wonderful and energetic presentation. You have covered the architecture very well, but you have made one strong statement that is what you say, we need to trust our engineers. Let me tell you, engineers are the most honest people. They don't have anything of an architectural creativity, they have numbers, they have formulas. If you're going to satisfy that, that is what they get into the hospitals. So definitely you need to trust your engineers. Architecture has its own advantages of doing things the way you want it, but engineers have the difficulty of doing what you have done. So that needs to be taken care of. Let me start my presentation by saying that, look, I come from Middle East for almost 3 decades of experience there. So my knowledge about healthcare in India is very, very limited in terms of numbers. There are specialists in the panel, and Dr. Desai can give you the numbers much better than anybody else. But I will not be a person who can give you the cost effectiveness as efficiently like others can do it in this panel. But I'll try my best to give you the knowledge of what we do there, and also the kind of quality and robustness and reliability what we can get into this. And the lion's portion of this particular engineering goes for HVAC. As she was talking about, 1/3 of the project cost goes in engineering, but in Middle East, it goes almost to 45% to 50%. That's what will be the cost of engineering in Middle East. So let's start from how HVAC design things, and how do we go about it, and what is the best way to do cost effective from this particular system. The air conditioning design generally starts with what we call it as HAP calculations. HAP calculations are like testing the patients with a stethoscope. It's the same thing for the building. A HAP calculation is one which is going to give you an early analysis program on the region based on the geometry of the building, the material of usage, and also its orientation, all on the building load, equipments, occupation, everything taken, and room by room, we develop something called as a calculation sheets for heat loads. These heat load calculations are essential, which again, Architect Nandini covered it very well, saying that it is very important to know what kind of an orientation of the building has to be, how much of an elevation has to be treated, and other things. These inputs are very much treated by the engineers in making it successful. So that the benefits of doing this is to ensure a precise sizing of HVAC system in terms of the tonnage of air conditioning you are going to get, instead of doing a thumb rule system of calculation and doing an overcapacity or an undercapacity of air conditioning, reduce initial cost and energy wastages in future. This is what we do by doing this particular thing. And again, standards are the ones which come into play. ASHRAE 90.1 and ASHRAE 170 is one of the documents which are very essential for doing this ventilation calculations for the HAP calculations. So the major parameters which are required for HAP calculations are multiple. I'll start segment by segment to explain this. One is called the R values and the U values, which are required for the external facade of the building, and the air volumes for the internal space calculations. R value measures the thermal resistance. Higher R value means better insulation against a heat transfer. So whatever the material we are going to use for the construction of the building or the periphery, that has to have a resistance value very high, so that it is going to give you a kind of a condition within the building which is going to be, doesn't require more energy to either increase the temperature or reduce the temperature. So the R value calculation is basically the thickness of the against thermal conductivity, the K values for each layer summed up in a composite facade. I'll explain that facade composite, how does it look like. And U value is what is the inverse of that. U value is inverse of R value total of all the materials which are used for the construction of the material of the particular wall. So generally, when you see a wall of an external wall, the inside and outside, you have a wall which has a thickness of cement plaster, and there will be insulation material which is in the middle, and then the internal plaster. So based on that, we do a calculations of what is the R values, and based on the R value, you get a U value. In Dubai, we generally have a maximum U value of 0.57, whereas I was going through the documentation of India, ECBC, it says that 0.4 for so places here, so the requirement of these materials have to be much more stringent to get somewhere closer to 0.4. Similarly, if you use a glazing material, this also has its own calculations. You can see the rock wool boards, the thermo blocks, airspace resistance walls, what is to be done, so that you get a U value of 0.29. Now the third important is for the space. The space requires air changes. Hospital industry doesn't work on comfort air conditioning. Hospital industry works on displacement of air. If there is no displacement of air, contamination is going to remain there. So when you do number of air changes and keep the air changes calculations correct, that is where you are going to get an efficient hospital building, healthy hospital building, robust and reliable hospital building. That is what we have to work on, not on the air conditioning. So eventually what happens in certain areas, like for example, an operation theater, which is 40 to 45 square meters, 2 to 2.5 ton air conditioner will be sufficient to have the cooling what is required of 21 degree plus or minus 2. But we cannot do that in that because we need 20 air changes or 25 air changes. So eventually the load of that particular air conditioner, which is used for AHU, used for operation theaters, goes up to 7 tons. I'm not reading everything because I left it on the screen so you can have a look at it. Yeah. So as I said, the HAP calculations will be having the weather parameters of the place where it is going to come, the window construction, the wall construction, and the space inputs. All this incorporated, we get to know what is the total tonnage, and also helps in every individual room, how much is the air conditioning required. So this helps the HVAC designer to look at how he's going to distribute his air handling units, whether to have a unit which is going to complete zone or separate the zones. All these are going to be possible by doing this kind of a calculation. Second thing, and the major important thing about cost efficiency comes is the clinical and non-clinical aspect. Clinical areas, as I said, it's governed by the standards and guidelines. There are reasons for doing it. We will touch upon that as why the temperature has to be that, why humidity has to be that later. So the clinical areas, you cannot do much of a change. Whereas we have non-clinical areas, along with clinical areas in the hospital. So a designer should be sitting with an architect and, as what we were talking about, identify the zones so that the non-clinical areas, we can look at the temperatures which are different from the clinical areas. If you are going to have an intertwined air handling unit, which is supplying to your clinical area and non-clinical area, even if you say, I'm going to set a temperature of 27 here, and I want 22 in my clinical space, it's not going to take it because engineeringly it's not possible. You need to have a separate unit for the non-clinical areas, and you need to. So when we are doing this activity, and if you are looking at a cost saving, architects has to spend time with the engineers and separate these areas so that the units can be separated to give this kind of conditions of 25 to 27 degrees centigrade and where 21 to 23 degrees centigrade is required. Of course, we all come from tropical region. We are very comfortable with somewhere between 25 to 27 as an air conditioning. Basically, what we are comfortable with is we don't sweat. That is what we call it as comfort air conditioning in this region. Now coming to the important aspect of clinical air conditioning, that is relative humidity and temperature parameters, isolation room designs, more critical because we all have gone through a huge pandemic and we understand how crucial it was to have an isolation rooms. Without isolation rooms, how difficult it was to run the healthcare facilities. And as I already touched upon, air displacement and filtration, which I'll be taking it further in this. So temperature and relative humidity. What is the purpose of having a temperature of 20 to 24 degrees centigrade and 18 to 22 degrees centigrade in operating rooms for thermal comfort and microbial thing? Similarly, relative humidity, 30 to 60%. WHO talks about 40 to 60, whereas ASHRAE talks about 20 to 60. So overall, 60 is the thing which is we consider as maximum. So relative humidity is one of the major parameter for clinical aspect, because if humidity is high, microbial contamination is higher. And that is the reason why the temperature of 21 degrees centigrade is required. That will avoid humidity to go down to 50%. And that is why we do this particular relationship between relative humidity and temperatures. Whereas if you go with the temperature of 27 degrees in non-clinical areas, achieving a 60 to 65% humidity is going to be challenging as per the psychometric charts. Isolation rooms, as everybody knows, the number of air changes required in an isolation room is 12 air changes. We need to have negative isolation for rooms where infected patients are going to be there. And then the protective environment is going to be immunocompromised patients are going to be kept. Both of them are exactly opposite in its function. There are so many parameters which we need to take up in a robust design of an isolation room, especially the negative isolation room. Other than just the ante-room and a room and air conditioning, negative extract, and generally what everybody does is, let's put a filter right on top of the patient and it is going to be useful. No. A healthcare facility should not be also become a hazard for the staff who is working there. If a service engineer has to remove that HEPA filter, he is going to be contaminated because of that particular filter which is infected by people and he has to work with it. So the engineering has to be also to take care of the staff requirements. So generally these units are called as bag-in, bag-out filters. These bag-in, bag-out filters have to be kept on the roof level or if level where service engineers can go. They just have to put the bag, push the filters into it, and then they have to discard it or burn it. It should never be kept inside the isolation room. And these are the three major areas of engineering which is challenging for air conditioning. One is the surgical department, other is the compounding pharmacy. I know this is something which is a new and a developing field of happening for hospital industry, though pharma industry has gone through this for decades together, but healthcare hospital industry is now coming into compounding industry in a big way. And medical labs and epidemiology lab are another area where IVF is very crucial. We have to have the filtration systems and other things which are required for that. So, surgical department, laminar hoods. There is no other best way to control the environment in an operation theater other than a laminar hood. A laminar hood is going to give you an air supply which is directly onto the patient. The first point of contact will be the patient, so that whatever is the contamination is going to be generated within the operating room is not going to be on the wound of the patient. Now, that will help, if at all done very well, we can reduce the amount of antibiotic given for the patient pre-surgery and post-surgery, and that can help in also recovery systems better for the patient in the surgical department. So there are, again on arguments, ASHRAE also justifies two types of operating rooms. One is with 100% fresh air, other is with a circulating system with HEPA filters. Now we have done this exercise in Dubai as to understand how effective is it to have an operation theater with HEPA filters and how does it look like in terms of energy saving. So if you see, both are operation theater same. One, A2A is that of within recirculating system where we have done 70% of recirculation system and 30% of fresh air, whereas A2B is the one which is with 100% fresh air. So you can see that the fresh air flow is 975 liters per second in our A2B, whereas it is 255. So overall the chilled water flow also varies this much. And these were the calculations which were done on a physical 2 operating rooms in the same facility to prove the client that, look, you have to change your operating room from your 100% fresh air to this one. And eventually we came up, I have changed the numbers to USD for easier understanding. If not, it was 450 dirhams per tonnage is our costing or annual maintenance. So you see, with a 70% recirculation, we are talking about $4,000 as an annual expenditure, as against 100%, which is going to be 11,000. Now, in this, the important factor comes in, okay, we are saving 11,000, say somewhere between 7,000 dirhams in this process, but how are we going to ensure that a filter which has been used, integrity is right, whether it is working well, how are we going to prove that? There are procedures and testing methodologies which we need to follow, and there are types of filters which are going to be used. MEP filters are the ones which are used for the general purpose, outpatient clinics. MEP 14 to 16 can be used in areas where the particle counts have to be of 1 micron, 0.3 to 1 micron. HEPA filters is where 99.97 particles greater than 0.3 micron particles to be removed. That is, we are used in operating rooms and ICUs. And ultra pure air is going to be used in much more complicated areas where we talk about the clean rooms which are coming up in compounding pharmacy right now. Now, again, I want to clarify or justify why HEPA, why not MEP 14? Both look similar. Why 99.97? Why not that 0.3? Same thing. Can you tell me how much is the size of a microorganism? Microorganisms are of a size of 0.1 to 0.2. But we are talking about a filtration of 0.3 and above. That is what we filter. So, how does this happen? It is not we are trying to take the microorganism as such. Microorganisms don't travel on their own. They sit on a particle, and that's the reason why we have to calculate it along with that, and that's the condition why we have classified air conditioning with a 0.5 micron. All classifications of air, of clean thing is of a 0.5. Though microorganisms are smaller than 0.5 microns, they cannot travel on their own. They have to sit on a particle to travel. That's the reason why the filtration classifications of class 100, class 10,000, class 100,000 is based on that. As I said, there is a pharma industry of India is very good at doing this, which we call it as DOP testing, dioctyl phthalate testing, wherein the aerosol of air is done on the top of the filters, and we check for the filter media damage if there is anything. Sealant to frame, any bypass is happening because of the gasket leakage or anything. Frames and grids are also being tested. The same thing need to be followed. See, we save for quite a bit of money there, but also this integrity, if is not checked, it is as useless, because if the HEPA filters are not tested, pressure differentials are not being monitored, and we don't do DOP testing of these filters at regular intervals, we will not be in a position to say that it's a robust design. So this is what I was talking about, the clean rooms. The clean rooms are generally classified with two particle sizes, 0.5 micron and 5 micron. So if you see, the classification grades are A, B, C, D, or you can read that as ISO 5, ISO 7, and ISO 8. And in US federal thing is called as class 100, class 100,000, 10,000, and class 100,000. That is the classification. And the particles which are going to be counted should be not more than 20 at rest and 29 in, sorry, you can see 0.5 micron, 3,250 is acceptable, and 20 for 5 micron is acceptable at rest time, and it is going to be more at the time of active operations. Now, where are we using this? Right now, USP 800 and a 797 have come into picture for chemopharmacy and IP pharmacy for total parenteral preparations. It has become a standard and a norm to use these kind of clean rooms where we have to follow the similar philosophy what is followed for preparation of injectables in the pharmaceutical industry for extempore preparations. So we have the same system of gowning, dispensing, airlock lobbies, and medicine preparation area. And that medicine preparation area in a chemotherapy unit will be having biological safety cabinets of grade B, which have to be level 2, has to be used for this purpose, and which will be having its own duty and standby high plume fans, exhaust fans. Similarly, 797 is for compounding pharmacy, as I told you, for total parenteral nutrition. This standard has come into picture active from November 2023. So it's still catching up, and it is going to be prevalent in all over the world when it is going to be for cancer patient treatment. A typical wall paneling, how it looks like in a clean room. There are three different materials which we can use for clean rooms. We can use GI, HPL, or GRP. Doors and windows of a clean room. This is what we call it as a dynamic pass window. So this particular pass box is not just a kind of a hatch for supply of goods. As we open the door, there is a HEPA filter on the top of it, and there is a filtration of air happening so that there is at no point of time contamination from, say, class 7 will be going into class 8, or class 5 contamination is going to come into class 7. Similarly, retinate ducts are become much sleeker, so they can be like a panel which is within the system, so that they are not protruding out into the area of working. These are the crossover bench. It's a very simple phenomenon of a crossover bench. It can be done even in the change rooms of hospitals. Right now, hospital change rooms are one area where people go, remove their shoes, put on this internal shoes in the same place. It's not acceptable as per the guidelines. It has to be like a crossover bench. You need to remove your footwear outside, turn on, pivot over, and get to the other side and use the, another footwear which is for internal usage. So these are few of the examples of clean room environment which is going to come as a future in healthcare industry, especially with the amount of treatment of cancer happening right now. Laboratories. Now, ASHRAE has one interesting document which is called as LACS, Laboratory Airflow Control Systems. Now, this is not just limited to healthcare industry. This is for the entire laboratories, right from school labs to the microchip laboratories. However, they have these classifications have been, sorry, it's time? Oh, I need to rush. Okay, so basically there are classifications. So our biochemistry lab, microbiology and histopathology falls in a level of VSDL 2 and 3. So if at all we want to do cost containment, we have to separate these laboratories and try to do the engineering accordingly. Let me show you how complicated an engineering of a laboratory looks like. If a single laboratory is going to be done with all these parameters, it is going to cost you. So ideally, microbiology and histopathology to be separated out and try to reduce your cost by doing the system of microbiology and histopathology different from the biochemistry laboratory. So coming to the last aspect of air conditioning, that is air handling of ducting work. Ducting plays a very, very major role because it is the network of air conditioning everywhere. Now there is a debate goes all over whether we can take a free plenum return or whether we have to do a ducted return system. It all depends on what clinical areas and non-clinical areas you are supplying, if at all we can identify, and how well we can maintain the areas without having any contamination above the ceiling. If at all we can do that, we can look at plenum returns. But ideally, ducting return is going to help also in terms of fire containment systems, not only just hygiene. So I have to rush quickly now, so I'll be running through this. So there are one more important parameter at the time of project stage while commissioning the hospitals, importance to be given for duct testing. ASHRAE has a clear guidelines for duct testing called DW. This is MACNA standard of DW 144, which tells you for what are the classification, how much of pressure has to be given and how much of Pascal and velocity of air, and we have to check the leak rate of the things. And there is an arresting system, There is an arrest system called as aerosol duct seal. which is just a kind of you need a small puncture and put the aerosol into it and seal the whole duct and improve the efficiency of ducting. If you are going to do this activity and keep it, your engineering, your energy cost of the healthcare facility comes down dramatically, because most of these ducts in the shaft are 60 to 50% efficient. If you are going to have the sealing done, you are ensuring that you are not doing too much of air conditioning, because you're not sucking the air from the shaft areas and above the ceiling areas, and it will improve your, we have not yet done a study on that in terms of how much of cost efficiency it has come, but we'll definitely do in future something like this. We want to do a white paper on this. So for the use of building automation systems, integrated not just to air conditioning, we can do it for lighting industry and other industries, and we can help in getting energy efficiencies. Departmental efficiencies. In fact, one of the hospital where I'm being a consultant, it's been given like this department, your energy utilization is this. So every week they get a report and they are told to work on it. So it makes very, very interesting for all the nursing staff, doctors working there to take care of the energy requirements right from water supply to air conditioning and lighting systems. Solar power is another one which we can definitely use in hospitals. Power saving is ultimately the goal of cost efficiency in a hospital in a robust air conditioning design. Plumbing also similar, stacking plants and other thing. RO water is required for your dialysis and CSSD, so let's limit. Again, I'm saying dialysis is a different, it's an industrial grade dialysis, RO water, and the RO water which is required for your dialysis is for human usage. It can be separated and we can cost effective. So I stop here. Thank you.